At the end of the period.
Okay, so I got a question for you. This is pretty cool. We got some good stuff to talk about. There's a ways I can take this off in some weird directions that you think are pretty cool. So close those suckers up. I got important things to talk about.
Close those out.
Close those up.
Is you're
Close those up.
gonna teach me how to
Close it up, Ian, stop talking.
Close those
Bring a
up.
fork just for Pi Day.
Yeah, I have a pie, it shouldn't.
If you have a fork, just continually just kind of jab yourself in the
Can I
arm
eat my
with
pie?
that fork. Keep yourself away.
Sideways for long.
We've got some pie. You guys, I'll let you all eat some pie at the end.
Well, I
Are
haven't
you guys
eaten
done
pie.
eating some pie?
I've got my pie, which is
Okay.
like almost all is still here.
Okay, so that everyone can have a little pie from. All right, so to celebrate Pi Day, you guys all understand what the definition of pi is, right?
No. Yeah, it's
We got it.
157 divided by 50.
No, it is not.
No, it's 20. No, it's 22 divided by 7.
Okay, pi is something really important. Pi is one of the most important constants in the universe, and it's got a very simple definition. If you take for any circle in a flat space, right? So we got to assume we're in a flat space, which we are in a relatively flat space in this part of the universe where we are right now. Now, if you're in a place that is warped strongly, this doesn't work. And I'll give you an example of that in a second. But in a flat space, we might call a Euclidean space, pi is given by the ratio of the circumference to the diameter of any circle, which is pretty cool, right? That's a pretty cool thing that there is that ratio like that that's going to give us this constant, right? We can see that from, what's the circumference of a circle?
See.
What is it?
2 pi
Oh.
2 pi r. Well, what's 2r equal to?
2r equals to.
Yeah, diameter, right? Twice the radius is diameter. So then isn't pi, if I just divide both sides by d, it's just c divided by d, right? So it's the ratio of the circumference to the diameter, and that's really what it is.
Oh,
Wait, so could I change?
No, it
But
doesn't. It seems like it would, right? Because the circumference and the diameter, the circle gets bigger, right? But the thing is, it always stays the same, which is what's interesting.
Is that just because they're related, like diameter relates to circumference?
Yeah, in that way.
I like
Huh.
Yeah.
sleep.
So this works in a flat space, but it doesn't work in, like, for example, a spherically curved space. Because if you were to do the same calculation for, let's say, the rotational or the orbital path of Mercury, it's not exactly circular, but pretend it was. I mean, it wouldn't change anything if it were. If it were exactly circular, then you would calculate its circumference divided by the diameter of that, right? And all we're doing, if we look at, let's say this is the sun, and let's say this is Mercury orbiting the sun, so isn't that just the diameter, right? And this distance is the circumference, right? If you did that calculation, if you did c, the circumference of Mercury's orbit divided by the diameter of Mercury's orbit, it would not equal pi. It wouldn't. It would equal something a little bit,
infinitesimally close to pi.
it would equal something a little bit less than pi. Yeah. Question?
What are the units for pi? Is it
No units, it's a number. It's a number. And look, what would the units be? Circumference would be measured, for example, in what? Meters. So then we'd measure diameter in meters, and they'd
Meters per
cancel.
meter.
Okay, see what I'm saying?
Yeah.
So, yeah, okay.
So I saw a thing that pi was almost 2. Is that just kind of a bunch of hocus pocus to you, or is there
Bunch of
history?
It's a bunch of hocus pocus.
Okay.
Yeah.
It was on YouTube though, so I mean.
So, there you go.
It's true.
Okay, so anyway, there's our justification for Pi Day. So what I want to think about today, though, is I want you to think about something. So how much speed does a force give to an object? Well, it's going to vary, right? What's it going to depend on?
Mass.
It's going to depend on, okay, it would depend on the force, I suppose, right? But if the force stayed the same, if two objects had different masses.
Oh, they wouldn't matter, wouldn't it?
If they had different masses, they'd get different velocities, wouldn't they, from the force? I mean, I could push on, if you're sitting on a bike and I push on you with a certain amount of force, you're gonna go. But if you're resting in a car in neutral, not gonna go as fast.
It's like pushing me on a bike, pushing Ian on a bike.
Okay, so So it's, I mean, you get the idea, right? So
That's what I'm saying.
So there's gonna be some difference there in the amount of speed that I'm giving to an object based on its mass, right? Okay, so then there must be a way that we can quantify that we can quantify the amount of speed given to a certain object by a certain force, right? There is. This is, I wanna show you something, and if you're in calculus, this is gonna be a little bit more meaningful maybe. I can take it a step further if you're in calculus. But, oh no, it will be.
Do this.
But you don't have to be. You don't have to be. I told you a little white lie. I told you that Newton's first law was force equals ma, right? I apologize.
Oh my gosh.
I apologize.
It's all wrong.
It's actually second law, so. I
No,
mean-
that's first law.
Okay, well, why does it say second law?
So, or second law, sorry.
Don't
Second.
question.
Yeah.
You're right, yeah.
What's going on?
It is. First law is conservation, no, it's not conservation, it's inertia, right? The law of inertia. Right. So Newton's second law tells us that force equals ma. Well, not exactly. It's pretty darn close. For most practical situations, it's a very good equation. You're not gonna know that it's off at all. But if you look on very extreme scales, this falls apart a little bit. And I'll talk about what those might be too. But the actual definition that always works is that, so this is not truly the case. Instead, we'd say that force is equal to the rate of change of momentum. That's denoted by a lowercase p, right? So what does that mean? So momentum p is equal to mass times velocity. That's all it is, mass times velocity. That's a useful thing, right? I mean, what's gonna have more momentum, a dump truck or a Volkswagen Bug? Very good, you got it. I was trying to trick you guys, but
Oh.
it does, depends on velocity, doesn't it? Right?
Don't you need time to find velocity?
No, velocity, I mean, we could measure that with a speedometer, right? Velocity is just a property of an object, right? Property of an object's motion. Okay? Like we might talk about, in our kinematics, we'll talk about initial velocity or final velocity. And we need the velocity at specific times, right? Okay, but I thought I would get you guys. Braden was
Too smart.
he's pretty
He's
wise.
in calculus.
That's
why he was able
Those
to.
are what we talked about today,
So anyway, yeah, so we don't know, right? I mean, it's a Volkswagen Bug that's traveling at 100 miles an hour most likely has more momentum than a dump truck that's traveling at 1 mile per hour, right? But if they're traveling at similar speeds, well, then the dump truck's got more mass, so it's got more momentum, right? And you guys have used, that's a word you've used before. You've probably never known what the actual physics definition for it is, but you've talked about momentum, right?
Yes.
You can use your momentum to do something, I mean, right? And you have an idea even that you have more momentum if you're going faster or if you're heavier, right? Or you're carrying something, right? Does that make sense?
Yeah.
You guys have a pretty good idea about that. Okay, so then let's do this. Let's do this calculation. So force is equal to the change in momentum over the change in time. Well, that's equal to the change in mv over the change in time. Okay, now here's where calculus comes in, okay, because technically we would be doing, if we want to do this not using constant forces and kind of contrived non-calculus ways, we would write this a little bit differently. So if you're not in calculus, don't panic. We're not going to do it this way. But if you're in calculus, this ought to mean something.
Just the word
It's the derivative of momentum with respect to time, right? So now let's think about what you would do if you want to take this derivative. Tell me what you would do, and we'll just reflect that back on the non-calculus calculation also. So if we're going to do this, this is like saying we know momentum is equal to the product of mass times velocity. So that's the derivative with respect to time of m times v. Well, how would I differentiate something like that?
Would you need to break up velocity into position
Well,
over time?
No, I don't have to. I can just leave them like this, but what's it gonna be? It can be a product rule case, isn't it, right? So we've got the product rule, so that's gonna give us m times the derivative times dv dt, right, by the product rule, plus dm dt times v, right?
Yeah.
Okay, well, we can do that up here. Let's do the same thing with deltas, so we're taking this in kind of a non-calculus context. All right, so that would look like up here then, that would look like m delta v over delta t plus delta m over delta t times v, right? Well, what's that equal to? What's the rate of change of velocity?
Acceleration.
That's acceleration, isn't it, right? So what force is really equal to then, if we look at it, take this equation right here, right? So force is really equal to ma plus dm dt, or delta m delta t times v. Okay, so I wasn't really lying that much, because this is normally a very, very small quantity. How in the world would the mass of something change?
The mass of something?
Yeah.
If something came and hit a planet, then it would have no mass.
Okay, but then you're actually, so if you're, it's a good idea. If you're accreting some material onto something like that, then that's no longer a closed system, because now that other material had some momentum before, see what I'm saying? So you've changed the picture then when you add some more mass, some external mass into the system. It's a different kind of change. I'm not suggesting that you're going to add or subtract mass from the system, like from the outside. I'm saying, how could, for example, the mass of this pen fundamentally change without adding or subtracting anything to it?
Oh,
No.
If it's going fast enough.
It's going fast enough. Yeah, if it's going fast enough. If something goes really, really fast, here's how you calculate the mass. The relativistic mass of an object is equal to its rest mass divided by the square root of 1 minus v squared over c squared, or what's c?
Speed of light.
Speed of light. Okay. So if we were to go, and m naught, or m sub 0, just means the rest mass. So the mass of the object at rest, right? So let's just say we were going to go 99% the speed of light, for example. Okay, so then what would my velocity be?
99 MC.
It would be 0.99 c, right, if I'm going 99% the speed of light. So what would that look like then? We'd get m naught divided by the square root of 1 minus 0.99 c. Those are, I don't know why I put that as a subscript in there. It's kind of drunken. That's supposed to be an exponent. 0.99 c squared over c squared. Well, the c's are going to cancel, aren't they?
Yeah.
Right?
Oh, wait.
Right?
Is both of them on the bottom?
Because I'm going to get, when I distribute that, I'm going to get a 0.99 squared times the c squared. Right? So the c's will go away. Well, let's just see how much the mass changes. See if it's appreciable. So we'd end up getting, let's just say that our rest mass is 10 kilograms. Let's just see what we end up with. So then we would end up with, we start off with 10 kilograms, we'd end up with 10 divided by the square root of 1 minus 0.99 squared, which is about 71 kilograms, right? So your mass would increase by more than a factor of 7, right? So in that case, if we look back, and why am I telling you? I mean, this is not normal stuff. This is relativistic physics. This isn't the physics of anything you'll ever do. Even a bullet is really, really slow compared to the speed of light. Does the mass of a bullet change appreciably? No, not even close. A bullet is such a small, small fraction of the speed of light that it's not even, it's going to be really, I mean, almost unmeasurably small change in mass, right? But what this tells us then is that there really are, if we look at the physics of the universe, of the way physics really works, if you do get things traveling, which they do, if you get particles or objects traveling close to the speed of light, there are two things that the force does. It's either going to accelerate the object or it's going to increase its mass. When an object is moving pretty slowly, virtually all of that force is being funneled into accelerating the object, which is what we study, right? Because we study relativistic, or we study non-relativistic physics. When we study classical physics or Newtonian physics, we're talking about the physics of stuff that we could do in our classroom or talk. You see what I'm saying? Or the realm of the everyday. But if we get going really, really fast, well then now most of that force is funneled into a change in mass, and very little of it is funneled into an acceleration, because you can't ever exceed the speed of light. It's the fundamental speed limit. You can never get there.
Says it.
Said Einstein. And it's the truth.
What if I have it wrong?
Well, like
He's not.
an atom would tear itself apart because it's connected at the same speed of light. Isn't it?
Well, it would be, you couldn't, because something would have become infinitely massive. Like even an electron, if you were to, I think I gave you guys the example of when you take like a positron, right? Take something that's a positively charged antimatter equivalent of an electron. If you accelerate that down Stanford Linear Accelerator Center, it goes really fast. But you're investing in that one little bundle of particles. You're investing the equivalent of all of the energy usage of the entire Bay Area gets funneled into that one little packet of particles, and they still can't go the speed of light. They go pretty close, but eventually there's diminishing returns, because the more energy you pump into it, the heavier they become, but a decreasing amount of that actually goes into making them go faster. And at some point, you're trying to push the speed up, but the speed won't hardly go up. Instead, you're just increasing the mass, right? That's the way physics really works.
So if the sun exploded, would it still take like 7 minutes for this?
Yeah.
We got
So-
7 minutes to live.
Anyway, so we got into some kind of, those are sort of the weirder sides of physics, right? The relativistic, the extreme parts. And so you might be thinking, well, this wasn't really any good. I mean, this what I told you it doesn't mean anything. Well, it does. It does mean something, because it's the way it actually is. And even though for normal physics situations, we could say that the change in mass is so small that it's negligible, and this sort of collapses into Newton's second law that we love and have used all the time, right? We all love it, right? Right. If we start off with this one, it does give us some insight into some things that happen in the everyday world, right? So actually, I probably want this one right here. Let's go back to this formulation of Newton's second law. Okay, so we've got F equals the rate of change of momentum. Okay, we can use this to explore some interesting things. We can use this to explore, for example, like car crashes. And this is one of the things I'm going to give you guys a smaller project to do in groups that we'll do over the course of like a week. But I want to teach you this first, because this is where we get the science of collisions, which is a big part of science. If you want to be a mechanical engineer, a lot of what you do, if you were designing cars, for example, would be built around this idea of being able to make crashes survivable by the occupants. And this is the physics you would be talking about and exploring. Okay, so what would happen here if I were to multiply both sides by delta t?
Then it would be increased by delta t.
So what would I get if I multiply both sides of this equation by delta t? I get F.
Delta t equals delta t.
Okay, let's do a little experiment. Yeah. You ready?
How many cars do you have?
What's that?
How many cars do you have?
These things?
Yeah.
Oh, lots of them.
Lots of them?
Not that many, actually. Okay, so data, they're all data. Okay, so here's what we're gonna do. So I've got some sensors. I've already calibrated these sensors. Did this at lunch today. And I found a couple things. I'm gonna write some stuff down here. We found that the mass of this cart is 0.508 kilograms. So let's write this down. So M sub C equals 0.508 kilograms. And I calibrated these sensors. I've got two sensors going on at once here. I've got a dual range force sensor. And what this does is when I tug on this thing, it's going to measure very accurately the forces that are acting on this string is transmitting to this little plunger, right? Okay. On the other side, I've got the force or the motion sensor that you're familiar with, right? So I'm just going to do this, and we're going to measure actually not the momentum. We're going to measure the force and the change in velocity, right? When I do this, this will be measuring the incoming speed and the outgoing speed, right? After this represents the collision, let's say, right? Sort of an elastic collision. And this is going to measure the forces that are occurring during the collision, right? All right, so let's see what's happening here. So if we go... Okay, so there's data. So what do we see here? We don't really need this top one doesn't do anything for us, but the bottom two are important. Here's velocity as a function of time, and here's force as a function of time. Okay? So let's do a calculation with this. So it looks like the forces start to happen. Can I draw a vertical line here? I think I can. Yeah. Like right about, I don't know, about there, let's say.
Yeah.
Does that look good?
Yeah, right there.
So right about there, we're going to get, I thought that was going to give me leave a line there. Maybe it doesn't. Oh, I don't need to, never mind. I thought that's going to leave a line. We don't need to. So anyway, I'm going to highlight a range of data then. So let's go from about there over to about there. Okay? So I'm going to look at a couple things. One thing I want to look at is the average force during that interval, right? It changes quite a bit, but let's go ahead and calculate an average. So I'll go up here to stats, and it tells me that over on that interval, the average force is 1.272 newtons. Okay? Let's figure out what the velocity is prior to the collision. So I'm going to highlight another little range of data here. Let's go kind of that spot right there, how about?
What does that spot do?
And I'm going to find out what is that average velocity right there, right?
Why'd you put it there?
Because that's good question. Why did I pick right there? Well, because
Right before it is.
yeah, because these all line up, right? All these time axes are the same, and so we can see that right about there is where we start to, the force sensor starts to apply some force, and so we want to go right before that to see what the incoming speed is, right? And if we calculate an average, there it is. We get about negative 0.7024 meters per second. Okay. Well, let's do the same thing over here. Let's go up and calculate afterwards what the average speed is. Okay, and we get something like 0.6011 meters per second. Okay, now let me ask you something here. Does that seem, ideally, what would you maybe have expected the speed to be afterwards? The same, meaning opposite, right?
Yeah, opposite direction.
Okay, so we're going to talk more about this in the next week and a half or so. But if this collision were what we'd call elastic, if this were a truly elastic collision, so no energy was lost, wouldn't you expect to get out all the energy that went into the, and we haven't even defined what energy is yet, so this is coming ahead a little bit, but you can see that maybe something happened here, so something was lost during the collision, right? And we'll talk more about that later. But that's really all the information we need. We could take this information and we could go back and do some calculations with it. So I'm just going to pull this over. You guys can't see it here, but I can. So I can grab this data off of there. And let's go back to here. And let's do some calculations. So we had two quantities that we were looking at, right? When we we divided both sides of this equation by, or multiplied by delta t, and we got these two different things, right? We got what we call impulse. F times delta t is frequently what we call impulse. Which kind of makes sense. Think about what an impulse would mean. If an impulse is going to be some brief application of force, right? So that's really what this is. You're going to apply force for some period of time, and the product of those two things we call the impulse. This is just a change in momentum. Okay? So let's calculate these two quantities for our experiment and see what happens. Okay, so there's the mass. The incoming velocity was negative 0.7024. So V naught the final velocity was positive 0.6011. Okay, so let's use that information to calculate the change in momentum. What's the initial momentum going to be?
0.
No. Momentum is just mass times velocity, right? So it's going to be the product of those two things, right? Do you agree?
Yeah.
Okay. And then the final momentum is going to be given to us by the product of those two things, right? Does that make sense? Okay, so we can look, put those on the calculator. How about? Let's see what those are. So initial momentum would be 0.508 times negative 0.7024. Don't do that. So there's the initial momentum, right? What would the units be? What would the standard units be for momentum?
Pounds per square inch.
Well, no, we've got to use regular scientific SI units, MKS units, right?
Meters per
Kilogram meters per second. Units of mass times units of velocity. And we don't give momentum a special name. We just call it kilogram meter per second. So there's the initial momentum. Final momentum is going to be 0.508 times what? 0.6011. And that gives us that answer, right? That's our final momentum. So if we want to calculate the change in momentum, isn't that just going to be the final momentum minus the initial momentum, right? So they add up to 0.662178 kilogram meters per second. That's the change in momentum, right? Okay, so let's write that down. So from our calculations, delta P is about 0.662 kilogram meters per second. Okay, let's also calculate what the force time, average force times time is. So the average force is, from our calculations, is 1.272 meters, or newtons. Is that what it said, 1.272? 1.272 newtons. Okay, if we look at our data here, I gotta pull this back over here. So this guy goes from where to where? So from there, I should have calculated or grabbed that earlier, but there's my change in time. So it's about, what do we got here? 0.539. Okay. Okay, if I multiply those two together, what am I going to get?
Let me see. 0.6. Something.
It's a pretty good guess. So 1.272 times 0.539 is about 0.6568. Okay, so those are pretty close, right? So our change in momentum was positive 0.66, and our change in our impulse was about 0.68, same units. A Newton times a second, think what that's really going to be. A Newton times a second. A Newton is a kilogram meter per second squared, right? Units of mass times acceleration. So we'd get kilogram meter per second squared times a second. Well, that would just cancel one of the seconds, and I'd get a kilogram meter per second, right? Because these are on the bottom, right? Okay, so how about that? They do experimentally turn out to be almost the same, right? So that's what we call the impulse momentum equation, and that's true. Impulse is always equal to the change in momentum. Why do you suppose that a little more force was applied than the corresponding change in momentum?
Something to do with the rubber band.
Why do you? It does have a lot to do with rubber band.
Yeah. Ow, that knee.
Oh, why do you think maybe something was lost there, maybe? Right? Because a certain amount of force was applied to the cart, but the change in momentum was a little bit less. What do you think may have? Friction? What else might have happened?
The universe moved.
Well, the universe is always moving. What do you think would happen if you measured very precisely? If you measured very precisely how to do that. That's if I measured very precisely the temperature of this thing, if I flexed it like this, what do you think would happen?
Probably like warmer.
Oh, you're the
If I do this a bunch, it's gonna get. It does get. You can feel it gets a little bit warmer if you do this over and over and over again. It gets a little bit warmer. That's why, like for example, that's why the moons of Jupiter are likely to have life, because they're so close to Jupiter with such a massive planet that they're constantly being tidally flexed, and that squeezing of the planet creates a lot of internal heat, which would keep the water liquid inside the planet. Right. So they got this big thick ice shells, but probably there's some liquid water in there on some of those moons, which might support life.
Wow.
But that makes sense though? That maybe something is being lost here because you're heating up the rubber band a little bit in the process of expanding it and contracting it. And so a little something is lost between the force that's applied and the corresponding change in momentum,
So
right?
how would you fix that?
Um,
Ultra rubber band?
yeah, right, exactly. What you'd want to do is you'd want to engineer some material. Maybe this is something you guys will do. You'd want to engineer a more highly elastic material that gives you back more of the force that's input, right?
Better slingshots.
Right. And that's part of, that's what structural and mechanical and materials engineers would do. That's one of the things they do, is they would try to take a certain property of a substance and maybe try to recreate the substance to engineer it in a way where it would be, for example, more elastic. Like the guy that first invented Super Balls, that's, I mean, really where that probably came from is some guy was doing some research trying to come up with highly elastic materials. Oh, hey, what happens if I throw this around the lab?
It's a
Sell
super
that in the store.
bouncy.
Super bouncy ball?
Yeah.
They have those?
Yeah, it's called Super Bowl.
What?
Dude, those
So
are
like
bungee
bungee
jumping.
We don't go.
You ever seen those little, they just go, they really go.
Yeah.
You throw them around the room and they just dart
Just give them
around.
a little toss.
Yeah.
I think we need to look up on the show.
Yeah.
I don't
Yeah.
do
So
it.
like bungee jumping, is it meant to absorb some more of it, or are they trying to make it elastic?
So you're gonna want it to absorb some of it, right? Because otherwise, if it didn't absorb any of it, what would happen? Well, no, you wouldn't, you'd go right back up to the bridge and you just keep doing that. You do that for a long, long time.
You just go down and come back up, you land.
Theoretically, but you could also hit your head on the bridge and, yeah.
That's your
That's true, that's true.
liability waivers.
And no matter how hard they try, they're not gonna,
Is there a perfectly elastic?
no, there isn't.
Not
There isn't.
yet.
No, you can find things that are fairly close.
Why is it? What's different?
Rubber is really good, actually. Rubber is pure latex rubber is very elastic.
What's keeping us from making it?
Physics. I mean, there's gonna be, anytime, we'll, as the year progresses, we can keep exploring that question. And there's things going on internally in the materials that are going to cause some energy to be liberated. When we talk about energy, it'll make more sense, and that's coming up. Energy makes everything better when we talk about energy. All this stuff gets easier and it gets more understandable. So, anyway, Time to eat some pie, probably, huh?
Osmosis, I got
I've
all
been,
that.
I've been.
Osmosis, it's diffusion. Obviously, you don't take bio.
Yeah.
You know where we're at.
We have it,
Do I have a dollar?
Yeah.
Okay, I'm taking a pie with me, so if you're in a meeting then.
if you guys wanna, you may have a little of this